Hello and welcome back. Today we'll be looking at the example of what is not a vector space. And the example I'll be considering is the set of periodic functions that is given over here. I'll explain what this means, but first of all, consider our bigger original vector space as the set of all real functions. Now the set of all real functions we have already established via previous examples that this thing is a vector space and it's a vector space over the field of real numbers. Now consider a subset of all real functions, that is the set of real periodic functions. So a periodic function is something that repeats itself over an interval. So after a certain interval, this function will repeat itself, and that info is encoded by this equation over here. F of x is the same as f of x plus p. So if you have some point, let's say this is the function graph, if this over here is x, then after an interval of p real numbers, you will see that it will start repeating itself. That's what periodic functions are all about. And so if a function is periodic, there will 100% exist some positive real number such that f of x is the same as f of x plus p, and this equation is valid for all real x. Now my question is p a subspace of all the real functions? Okay, so let's see what all things need to be established for this. Firstly, the set of all real functions is already established as a vector space, and hence proving that the set of periodic functions is a subspace boils down to just three rules. First is the identity must exist inside the set of periodic functions. So the identity function, or the additive identity function actually, it is the function which is 0 for all real values of x. Alright, that's the identity function. And now obviously any positive real number will actually serve as the period for this thing. So if I consider any p equal to 0, or p greater than 0 actually, suppose let's say I consider p as 1. So 0 of let's say x is the same as 0 of x plus 1, because both of them are anyway 0. And so any positive real number can serve as the period for the 0 function. Now what about closure under scalar multiplication? That's also easy to prove, because if I multiply any scalar a, then all it does, it just scales the values of each f of x. So if I have a function that looks like this and if I multiply it with a, all I'll do is just scale the values. I won't do anything else. All I will have here is a times f of x. So it's, again, how does that affect the periodicity of this function? It does not. Short answer. Because if f of x is f of x plus p for all x belong to real, then if I multiply a on both sides, a times f of x and a times f of x plus p both yield the same values as well, and hence a times f is also periodic with a period of p. Okay, so this is where it was simple until now. Now comes proving whether it is closed under addition. And let's see, how do we exactly prove that f1 plus f2 is also a periodic function? Okay, let's say that f1 plus f2 is a periodic function. I'm assuming in this case, and I'm assuming that it has a period of t. And f1 plus f2 individually, they are also periodic functions, and they have a period of t1 and t2. And t1 and t2 is not equal. Okay, so if t1 and t2 are equal, then obviously f1 plus f2 will also be a periodic function with a period of t1 or t2 as well. But in this case, I'm assuming t1 is not t2, and the next assumption is that f1 plus f2 is a periodic function with a period of t, in which case f1 plus f2 of x is the same as f1 plus f2 of x plus t. Now this thing can be split into f1 of x plus f2 of x, and the RHS can be split into f1 of x plus t plus f2 of x plus t. Now this thing is valid for all x belong to real, mind you, this is important. And so if I club the f1 terms and f2 terms together in the LHS and RHS, then I'll get this equation. F1 of x minus f1 of x plus t is the same as f2 of x plus t minus f2 of x. Now I'll just call this as h1 of x and I'll call this as h2 of x. So a function minus a function is also a function, right? So in that case, h1 of x is the same as h2 of x, and this is valid for all real x values. And the next key step, this is the first key step, that is clubbing them into one group. And why I'm doing this is because h1 is f1 of x minus f1 of x plus t. Now notice that h1 of x will be periodic. It has a period of t1 inherited from the terms, that is f1 terms. So since f1 individually they are both periodic and they have the same period of t1, h1 will also be a periodic function with the same period. Now similarly, h2 is also like that, but it has a period of t2, and hence h1 of x is the same as h2 of x, and since they are both equal and h1 happens to be t1 periodic, h2 happens to be t2 periodic, both of them must be t1 periodic and t2 periodic. Now simultaneously this has to occur. They are both t1 periodic and t2 periodic as well. Now there are only two cases where something like this can occur. It is when t1 is a multiple of t2 or t2 is a multiple of t1. Like for example, if I have h1 of x is, let's say, 2 periodic and h2 of x is 4 periodic. So it repeats itself at an interval of 2. This repeats itself at an interval of 4. But you see, h1 of x is h1 of x plus 2. That's also equal to h1 of x plus 4. So by the virtue of being 2 periodic, it can be 4 periodic as well. So it can be periodic with a period of any multiple of 2. And that's why t1 is a multiple of t2, or vice versa. If h2 had a period of 2 and h1 had a period of 4, still would be valid, not a problem. Now the second case is when h1 and h2 are both constant functions. Now as I mentioned before, while proving the identity exists, if 0 of x is 0, then any positive number can serve as a period. This same concept is valid for constant functions as well. That is, functions which take a constant value for all real value x. Now in this case as well, any real number, any positive real number actually can serve as a period. Okay, I hope it's clear until here. So this was the second key step. Now the last key step is about this. Now if k is the constant that h1 and h2 are equal to, then obviously f1 of x is k plus f1 of x plus t. Now this I have got from the equation from h1, and from the equation of h2, f2 of x plus t is equal to k plus f2 of x. Now this stuff is valid for all real x's. And now this I can write it as this. So if I actually write it like this, then f1 of x is k plus f1 of x plus t, but f1 of x plus t itself is k plus f1 of x plus 2t, right? All I did was add t to the x's on both sides, and so that way if I do it n times, then I get f1 of x is n times k, because if there was only 2 times, if I did 2 times, it would be k plus f1 of x plus 2t. Now this adds up to 2k. If I do it 3 times, it will be 3k. Now if I do it n times, it will be nk. So f1 of x is the same as n times k plus f1 of x plus n times t. Now similarly, the same with f2 as well. Now notice that as n tends to infinity, the value of f1 of x will be f1 of x plus n times t plus n times k. So n times k will actually go towards infinity. So it will diverge in a way. Now the value of x1 is unbounded because of this. By unbounded, I mean it goes towards infinity or minus infinity, however you, whichever you want to say. Now note that in real numbers, infinities are not a defined value, and functions, whenever you map a real number to a real number, now that sort of mapping, this f of x will have a defined value. It will have a defined finite value in the real numbers. It won't be undefined values. And so if k is not 0, then obviously this thing will be unbounded. Now if f1 becomes, if f1 and f2 are unbounded, then obviously for certain value of x, their values won't exist. They will be undefined. That's what this unboundedness means. And so obviously we have to set k to 0, because otherwise your functions won't be bounded. And so in that case we have f1 of x is the same as f1 of x plus t. So t over here is a period for f1, and hence t must be some sort of multiple of t1. Okay, and similarly f2 of x is also f2 of x plus t, implying that t is also a multiple of t2. Now in this case, if I just divide both sides, I got the ratio t1 over t2 is n over m. That means that the ratio of the periods of the two individual functions f1 and f2 has to be a rational number. And that's the condition for periodicity in both cases. In both cases, that is, where did it go? Yeah. In case t1 is a multiple of t2 or vice versa, and even when h1 and h2 are both constant functions. So in that case, t1 over t2 must be a rational function, a rational number. That's the condition for periodicity. For the sum of two periodic numbers, periodic functions, to be periodic as well, the ratio of the periods must be a rational number. But not all periodic functions may follow this. So what if I have pi over e as the ratio? In that case, it's not rational, it's irrational. That means I can't add these two, whatever functions they are, with period pi and e. I cannot add them and expect the addition to be periodic. It doesn't work that way. And so your set of periodic functions, it's not closed under addition, and hence it's not a vector space. It's not a subspace of r raised to r. Okay, so this way I have proved that the set of periodic functions don't form a subspace. I have highlighted the 3 key steps of how to prove that addition is not closed in that case. Alright, with that I'll end my lectures on subspaces. In the next video we'll learn a new concept, and it will be theory this time. Okay, thank you, stay tuned, have a nice day.